Hello everyone, in this video I'm going to discuss the concept of time division multiplexing and frequency division multiplexing and solve a problem on each one of them. First, let's begin with the time division multiplexing. What does it mean to do time division multiplexing? Let's assume that I have a single antenna and I have 4 users and I need these 4 users to transmit their data to using this antenna simultaneously. Well, of course they're going to interfere with each other. Why? Because they cannot use the same antenna together. Only one antenna only one user can use the antenna. Okay? So it turns out that if it was a discrete signal, we can even improve this performance and allow for multiple users to use this antenna at the same time. How are we going to do this? Let's assume that these 4 signals are already discrete signals. Okay? And what we would like to know is what to do exactly in between the user and the summer, the adder, so that we can allow them to use the same antenna. What block shall we add? Okay. It turns out that it is just a shifter. Why is that going to happen? Well, if you take the first signal and you allow it to be transmitted, and then you take the second signal and the first signal you leave it as it is, the second signal you shift it by a very small amount of time, and the third signal you shift it by another small amount of time, and then the fourth signal you shift it by another amount of time, or a duration of time, and then you add them all together, then they're not going to be interfering with each other. Okay? And that's basically what you're going to be transmitting. You're going to be transmitting this signal. Okay? Which is the addition of all versions of all users, but after shifting them. Of course, it doesn't matter whether the samples are positive or negative, are they low or high, the values are positive or not, doesn't really matter. All what it matters where the position of each sample is. Each sample of them is, the duration between each sample is Ts, and that's why the bandwidth is calculated as 1 over Ts. Okay, then in that case you can, as long as the distance, the duration between each sample and the other is constant across all users and across all samples, then you can do this trick. And this is what is called time division multiplexing. Now, when you transmit this signal at the receiver is going to listen to all these samples. But if it was the receiver of the first user, of the blue user, then in that case I'm going to ask them to sample by Ts. Okay, so take the first one, leave 3, and take the second one, leave 3, and take the third one, and leave 3, and so on and so forth. So they're going to be sampling with Ts as well. Okay, so but right now, what is the bandwidth of the signal that has been transmitted? It turns out that the bandwidth is going to be multiplied m times the bandwidth of a single signal. Why is that? Because the bandwidth is always 1 over the value of the duration between each 2 samples. The medium does not differentiate between these 2 samples. The medium is seeing that the first sample is followed by another sample after a duration of Ts over m, okay, where m is 4 here, and the third sample is Ts over m as well, and so on and so forth. So this duration, the duration between each 2 consecutive samples, has been decreased. Okay, which means that the bandwidth is going to increase. Of course, you need to pay something at the expense of transmitting. This comes at the expense of the bandwidth to transmit multiple signals at the same time. Let's consider this example. We have 10 continuous signals. Okay, remember that these are continuous signals, and each one of them has a bandwidth of 4 kilohertz. Okay, so the maximum frequency that these signals can be transmitted with, okay, the maximum frequency in that signal is 4 kilohertz. Okay? So, and we need to multiplex all these 10 signals using time division multiplexing. So, and we'd like to find out how much bandwidth the entire signal is going to be consuming, right? And we're given two cases. One of them without the synchronization signal, and the second one with the synchronization signal. I'm going to explain what that is in a moment. Let's first solve without the synchronization signal, which is the straightforward example. Can I do the shift and then the addition right away, or do I need to first sample it? Of course, I cannot just do the addition right away. They are continuous signals. I first need to convert them to discrete signals first, each one of them, and calculate the bandwidth of that discrete signal, and then do the multiplication based on that. Okay, or in other words, calculate the bandwidth of calculate the duration time between each two samples in the signals. Okay, so right now let's look at the sampling frequency. How much sampling frequency can I sample each signal with? According to Nyquist theorem, I need to sample it with 8 kilohertz, and thus the duration between each two consecutive samples in one signal is going to be 1/8 milliseconds. So for the case of no synchronization signal, okay, and I'm going to explain what that is in a moment, then in that case the time duration between each two consecutive samples in the overall system is going to be 1/80. Where does this 80 come from? 8 multiplied by the number of signals. Okay? Alright, so that's in milliseconds. Okay, so right now these are the samples, and here I'm putting here 9 samples between each two consecutive samples. Okay? Okay, remember that sometimes but right now let's first calculate the duration. How do you calculate the duration? The duration is 1/, this number, right? Which means that it is 1/TSN, which is 80 kilohertz. Okay? That's a straightforward example. Okay, right now, what if you have a user that cannot know what the value of TS is? Okay? The user needs to be informed of this value of the receiver. Okay? So and that's why sometimes I transmit here a very large signal that I call the synchronization signal. What's the benefit of this synchronization signal? Its benefit is to tell the users where to start receiving. So the user detects this signal, and the user knows that he's the first user. So after the synchronization signal, he picks up the first sample and leaves a certain amount of time, okay, and waits for the second synchronization signal and decodes the second sample, and then waits for another amount of time until he receives the third synchronization signal and receives the third sample, and so on and so forth. This synchronization signal is done for synchronization, okay? But unfortunately, it's going to consume some amount of power as well as some amount of duration. And that's why you need to divide not by 10, you need to divide by 11, okay? Because the synchronization signal is considered one of the samples, okay? So without the synchronization signal, you divide by the number of users, okay? But with the synchronization signal, you need to add 1 to the number of users, okay? And the synchronization signal becomes a part of the signal that has been transmitted, and it is with a very high value so that users can know the value of this, the location of this signal, okay? And that's the case with synchronization signal, okay? Okay, let's move on to the frequency division multiplexing. Can I do the same thing, but I interleave them? I do the multiplexing in the frequency domain? Yes, I can. Let's assume that I already have a bunch of users, and there are 4 users as before, and each one has, let's say, 1 kilohertz. Bandwidth equals 1 kilohertz. Okay? And for the sake of simplicity, all of them have the same bandwidth. How can I transmit them together? And they're continuous signals. Okay? Do I need to do sampling right now? No, I do not need to do sampling. Why? Because we're going to be doing everything in the frequency domain. Okay, but how am I going to do it in the frequency domain? Well, the very first step is that if I add them, remember that if I add all of them together, okay, then they're going to interfere with each other, and I'm not going to be able to decode any of them. So what I need to do is that I need to shift this one, and shift that one, and shift them in the frequency domain so that I can do the addition. So let's do the shifting. So multiply by a carrier. Okay, so I'm going to multiply this by a carrier, multiply that by a carrier, and the carrier's value is equal to 1 kilohertz. So I'm going to shift it at 1 kilohertz. Okay, because that's the bandwidth of that signal. Okay, and then I'm going to multiply this by 2 kilohertz and multiply this by 3 kilohertz. Okay, why? Because this is at 2 kilohertz and this is at 3 kilohertz. So that's 1, this is 2, and this is 3. Okay, multiply by a carrier. Okay, and then filter only the right side band. Why? Because if I add them right now, if I add all of them right now, still they're going to be interfering with each other. So I need to only choose the upper side band only and remove the lower side band. So right now, if you pass them by a filter that filters only the upper side band, of course the filter has to be sharp so that it can chooses only the upper side band with a very precise way. Then in that case, you're going to be obtaining the upper side band only, and thus you can add them all together and obtain this signal. Okay? The bandwidth that is going to be used, consumed by the ultimate signal is going to be the bandwidth multiplied by the number of users. Okay? So here, this is the number of users. Okay? Let's take a look at another example. We're going to repeat the same example using frequency division multiplexing. And remember, we do not need any synchronization signal anymore because the synchronization is used only in the time domain. Right now, there's no need to do any time domain analysis. Okay? So no need to do synchronization in the FDM. And right now, the FDM, the frequency division multiplexing bandwidth is going to be 40 kilohertz. Remember that if you do not have that luxury of getting the bandwidth, of obtaining the right side band, while having like a very sharp bandwidth, a very sharp filter, bandpass filter, then in that case you need to shift each one of them by twice the frequency, by twice the bandwidth, not by just 1 kilohertz, but by 2 kilohertz. For the case of this, you need to shift them by 2 kilohertz. Okay? And for the case of that example, I need to shift each one of them by 4 kilohertz if I do not have that luxury. And that's why the bandwidth over here, if I do not have the luxury, if I do not have that filter, bandpass filter, is going to be twice the bandwidth of the FDM. Okay, which is this value, okay, which is going to be 80 kilohertz, okay, if I do not have that filter. All right? Okay, thanks for your attention. Please make sure to share this video if you found it useful. Other people might find it useful as well. And the document, these notes are mentioned, there is a link for these notes in the description of the video.